Okay, so we've talked about that use of weighting and using it in this hierarchical versus non-hierarchical tests. Make sure, if you have questions about that, ask me in class, because I want to make sure you understand this issue, and it's a little bit maybe esoteric at first. Gary assures us, though, at the top of the slide here, that if you only consider and compare classical hierarchical models, then you don't have to worry about your parameterization chosen. The reason is that the standard model in your ANOVA test that assuming that correct parameterization is the one that derives from looking at your simple averages. So exactly the way we've doing it all semester until this set of slides. When we use those weighted averages like we did in the rats example, we get other parameterizations, right? And so if that really is the correct weighting, then making non-hierarchical tests is valid. If that is not the correct weighting, then you should probably stick to the classical hierarchical models. And so in that rats example, we would have found no effect due to the antibiotic used in the classic model. But we did see an effective difference between, I think, 1 and 2. We didn't do the test, by the way. We're assuming Gary's right about that. This last comment just refers to this data, which I'm skipping because I don't like it and I don't like the data context, but do ask me if you have questions about it. So we've gone through a laundry list of topics, 2 so far in this section of the notes. The first one, of course, was single replication. Remember that at the start? Then we talked about this idea of hierarchical weighted averages and why we might want to entertain that in a factorial design. Now we're going to talk more about pooling. So the practice of removing non-significant terms from your model and just pooling them into the error or residual. Gary generally doesn't think that this is a good idea. The main reason is that it actually inflates your MSE, because if you're pooling those non-significant terms and collapsing them into your MSE, then you risk biasing your MSE upward. Now, this is very distinct to ANOVA modeling because I pool and drop non-significant terms in regression models constantly. But for a classical ANOVA model where you're assuming a model hierarchy, he really suggests not pooling. Again, I think I would pool only when the interaction was non-significant, and I felt like it was non-significant because it didn't make sense in some way, that there was some sort of theoretical reason that was happening. And I'm not sure what Gary's situation where pooling is advantageous is, but that would be my take on it. Okay, so Gary's take is that one case where pooling makes sense is where you have very few degrees of freedom for error. So the extreme case of this is, of course, single replication, where we have to pool or else we can't analyze anything in our experiment. But if we have a very small degree of freedom for error, it makes sense to collapse it into these non-significant terms into the MSE. So he says, consider pooling a term if you have very few degree of freedom for error, let's say less than 10 or 12. I'm not sure why those are the cutoffs, but that's what he recommends. The term has a low F ratio, so, you know, really close to 1 is what you want. So less than 2 is what he suggests. And if you're still maintaining the hierarchy, so if you get rid of an interaction term, make sure that the hierarchy for the interaction terms that you still include still exists. And I do have to say, maybe I'm less cautious about this than Gary, because I think this really does make sense. And then I feel very strongly about my significant terms that I find, because I know I have run the risk of inflating my MSE in this case. So you're being conservative when you do this, I'd say. Okay, so we're going to talk about pooling a little bit more with a reflection here. We've been talking all about balanced design. There's another situation where pooling is really in order, and this is where we have an unbalanced design. It can be tricky with an unbalanced design to examine your coefficients because the coefficients for terms in unbalanced models depends or can depend on what other terms are currently in the model, and that's kind of a chronic situation. So in this case, what you should be doing is selecting the terms to retain in the model using MSE from the full model. So this is with every term in there, the full model. Then secondly, pool those unselected terms into error before examining the coefficients on these selected terms. Again, this gets at that idea that you're being cautious when you do this, so you select those terms first using that smaller MSE, and then you pool those terms into the error that were not selected. So I think it's worthwhile to maybe spend some time on this. Okay, so we are going to spend some time in class talking more about unbalanced factorials. They can be really tricky. Gary starts out with the quote, "In every life a little rain must fall," which I think is a nice way to think about unbalanced factorials, because when you first are dealing with them, they can be a real hair-pulling experience. So remember, when factorial data are not balanced, that's where we have like those treatment combinations, those number of replications are unequal. So I'm going to show you an example in class where we have two research questions to answer using a two-factor model. It's really a simple 2x2 model, so it's as easy as it could be, but I think you'll find it a challenge in class. Some of the reasons you'll find this a challenge is the row and column contrasts are not going to be orthogonal. We're going to explore that in detail. There's going to be a distinction between choosing that hierarchical model and then testing those hypotheses about the parameters. And we have to think more carefully about it. It becomes somewhat of a philosophical question. And then because of this distinction between choosing the hierarchical model and which hypotheses we test about which parameters, there's so many different ways we can go about building that ANOVA model and constructing our test statistic. And we need to kind of tailor it for our research question. So I'm going to have some data. I'm going to have our code. So I do ask, since you're watching this video before class on Tuesday, to bring your laptops again, because just like class on Thursday, you're going to be working through this perhaps together in class. I'm not sure you need R for this. It kind of depends on what we end up doing, but it would be nice to have it, even though I'll have a printout for you to scratch your notes on in class. So ANOVA still provides a comparison between your model, your small model or constrained model and a larger model. And we can still deal with these straightforward comparisons even with unbalanced design. So this really is not too much of an issue when we start talking about unbalanced data. But we do need to think carefully in order to test a particular term, what terms need to be present in the model, in that base model, in order to, say, compare the models where we've included or excluded a particular term X. Again, I think let's try to incorporate this into our in-class example that we will work through. It's best learned by experience, I think. Okay, so most of the time in class we've just been looking at sum of squares, and I have not done any kind of explanation for different types of sums of squares, and now it's going to make become an issue for us. And let's kind of generate why we need the reason why we need to start thinking about different kinds of sum of squares within a modeling context. Let's say we have the following model. So notice we have 3 factors, and then we have two-way interactions between those 3 factors. So the terms in our base model are given here. We could start out arbitrarily, of course, with just term A. This would give us our overall mean, global mean, and then for the levels of A as well as the global mean, I should say. And that model with A would be compared back to the global model with only the grand mean. Then we could add in B, and that base model that we compare that to would have additional terms 1 and A, of course. So notice we're setting up a hierarchy. So we get to C, and the base model includes 1 and A and B. So hopefully you're seeing that pattern as we start entertaining the interaction terms that we add sequentially into the model. We have all of the previous terms in our base model. Using this kind of sequential building of the model, each term is adjusted for those that preceded in the model, or it's where that sum of square, in other words, is going to be adjusted for the presence of those terms that are in the base model. So this is the simplest way to do it, especially from a programming perspective, and that it is the default in pretty much every package I've worked with. It also has an advantage. Sum of squares for the individual terms will add up to sum of squares for the model as a whole, which is a nice, pleasant characteristic to see. It makes a lot of sense, makes us feel better about the model too. However, with unbalanced data, again, things get prickly. We're going to get a different decomposition for terms in different order. For example, if we add B adjusted for A, it's different than B adjusted for A and C. And so we need to be very careful and thoughtful, again, about how we do this. And in the context of unbalanced factorial, building the model means selecting your main effects and interactions that you need to describe the mean structure adequately. We want to build our model so it does not depend on parameterization. We've talked a lot about that model parameterization in this section of the notes. We need models that where the effects are not, and whether or not they're significant is not dependent upon that parameterization. And we also need to build models by comparing the hierarchy. Okay, that means for any term X, we choose as a base model the largest hierarchical model that doesn't include X. So this is a good way to go about it so that we're always partitioning that added sum of squares additional for a particular term X in comparison to that base model, with reference to that base model. So getting that base model is a little tricky. I think I'm going to stop here for now and talk a little bit more in the next set of notes about using different fitting constraints and then these different types of sums of squares that we're going to need to be able to think about.